little bit late, but not too bad. So we actually did we didn't call it compound interest, but we introduced simple interest problems last day. And so our main formula that we're going to be using is where? Here. Well, we've got two main formulas. I, which is the amount of interest, right? P is the principal investment, okay? Or it's the amount that you've borrowed or put into an account, okay? R is the rate, the interest rate as a decimal, okay? And T is how long it's going to sit there for. And then we introduced A, which is the accumulated amount after that amount T has passed. We sometimes call it the future value, A. So it can be the accumulated amount or the future value. So in terms of, I guess we can do a little bit of review. So for our review, we introduced what we call simple interest. Notice the difference. We've got simple interest and compound interest. So it depends on how the interest rate behaves, right? And that will determine which formula to use. And we introduced I equals PRT. And we just said where I is the amount of interest earned or paid. That's a dollar amount. P is the principal invested or borrowed. R is the interest rate as a decimal. We often report percentages, but for math, we need to work with the decimal value. Okay? So for example, 4%, we use 0.04. Okay, so divide by 100. And T is the time invested or borrowed. I'll move these guys down. We said that R and T have to match in terms of if the rate is per month, right? Then the time has to be in months, or if the time is in years, you can convert the rate to years, but they have to match. Okay. So these guys, rate and time must match. The next formula we introduced was A. Because it uses PRT, just like we have earlier, I'm going to put A up here and do a little arrow just so we can define them all in the same space because they use the same values. Okay? Where A is the accumulated amount after T. And T is however long you've invested or borrowed your money for. So the accumulated amount is either how much you have to pay at the end, including your interest, or it's how much you get at the end after you've made your deposit and waited for some amount of time. And so it's the accumulated amount after T, and it's going to be a dollar amount. And I guess I should say P is a dollar amount as well. I'll say AKA, also known as the future value. Oops. Clean that up. The future value of an investment or a loan. So then we have A, which if P is the, let's say we've invested some monies, right? It's more fun to think about because borrowing money, you just pay more and it's boring. But let's say you've invested some monies, P, and then after some amount of time, right, then you earn interest on that, some amount of interest, which means that the accumulated amount is going to be P plus I. And you can move between these, right? I is A minus P if you want, or P is A minus I, right? You can switch these around however you'd like, okay? But what you can do, notice that we have a formula for I, right? I is PRT, so if we replace those, right, we do a substitution, then we get A is P plus PRT. Now I have a common P. So A is P times 1 plus R times T. And that's how we get that formula that's on your formula sheet. This one's on your formula sheet, and this one's on your formula sheet. And I can't remember if I have let's see, where's the formula sheet? Oh, that's right. This should be capital I and capital I, but I do have the A minus P on there, which is a version of it. But I do have the future value on there. I'll say that I is equal to A minus P. And then I'll highlight that because that's on your formula sheet. We introduced some discounts, right? Some discount rates and things like that, which I said we will not be testing you on, right? And so I promised I won't test you on it, but there are some homework problems where it might be nice to know about the discount rates, right? And so it's good for practice, but in terms of testable questions, we'll only use these formulas for simple interest. So today we're going to talk about compound interest. Now, compound interest is more common. Okay? It's usually what banks do in the background. They don't really, they're not upfront about it. But if you read the fine print, it'll say how often it's compounding. Okay? And so what we saw last day, we did a little example where we said, okay, well, what if I invest some amount of money? Let's say I invest $100, and after a year, I've made $10 in interest. Wow, that's a nice interest rate. And so then, now at the end of the first year, I have $110. So then imagine if I just took that and I reinvested it, and then I made 10% on the $110 for the next year. And then I compounded, so I added that amount of interest that I earn, right, for the next year. What is $11? And then after the next year, I compound it again. So I keep adding the amount of interest that I've earned onto my principal amount. That sounds really, really nice when you're investing money. Not so nice when you've borrowed money, right? And so that's okay. They end up being fairly similar, okay? And as we'll see, okay? But simple interest generally is for short lending periods. Okay? So often if it's kind of just a quick loan, then they do simple interest and they don't bother with the compounding. Okay? And so let's see here. When money is loaned or borrowed for a longer time period, if the interest is paid or charged not only on the principal but also on the past interest, right, then we say that it is compounded. And so that's what it means. But if you think about the word compounding, right, it means to crush, right? And so then you're putting things together. And so you're compounding your principal with your interest that you've earned or have to pay. As an example, suppose we have $200 and we put in an account that pays 8% interest. At the end of 1 year, we would have $200 plus $200 times 0.08, right? Times 1, but because t is 1, but we can ignore that. And so we end up with $216. So now, and this is what we did in the example last day, what if we put that $216 into the account again? We don't actually have to do it. The bank does it for us, but it's technically what's happening. So then after another year, we're going to have 216 plus 8% of 216, right? Which means that we would have $233.28 in the account after 2 years. Now, I'm pretty sure. I thought I compare this to simple interest. If we just deposited $200 and we didn't every year check in to see, okay, and add on that interest. So then we have A for simple interest is P times 1 plus R times T. Now to match the scenario, because this is the A for 2 years compounding each year. So we want to compare the A's. The initial investment was $200. Times 1 plus R, which was 0.08, and T is 2 years. Do I have my rusty calculator? 0.08 times 2. Making sure you do the multiplication first inside the brackets. Plus 1. I get 200 times 1.16. $232. So like I said, these will be very similar, right? They're not going to be the same because they're behaving differently, but they will be very similar, right? $232 is similar to 233, 28, right? But it's slightly less, which makes sense, right? Because right here in this scenario, we were earning interest on the interest that we had earned, right? And so it makes sense that simple interest will be less than compound interest. A for simple interest will be less than A from compound interest. Which is awesome if we're the ones depositing money and we're getting interest. It's not so fun when you have to pay the interest, right? Because it's just building and building. Now this was over a pretty short time period, right? 2 years. But most mortgages are 25 years, right? And so over time it becomes quite a large difference. Nice. Now, this feels tedious, right? Check in every time that you want to add on the interest and change your P, and then calculate your A again, and then make that your P, and then calculate your A. We don't have to do that. We have a formula to do that, of course. But before we can introduce it, we need to talk about, I think I need more space than what I have there. Doesn't anyone need this page? We need to talk about compounding periods. Compounding periods are denoted by a lowercase n in our formulas. And so banks often compound interest more than one time a year. And so if we have a bank that pays 8% interest, but compounds it 4 times a year or quarterly, this means that every quarter the bank will pay interest of a quarter of 8%, right? Or 2%. So you take that 8%, which is for the year, and you split it up into the quarters. So you don't get 8% every quarter. You only get 2% until you've built up to the 8%. Now, we need to memorize everyone's favorite thing. A lot of them will be pretty straightforward. We need to memorize some common compounding frequencies. Of course, you can compound annually, where n is equal to 1. Right? Because we use a lowercase n to denote the compounding periods, or how many compounding periods we have in a year. What's our next one? We can compound semi-annually, which is twice per year, every 6 months. We can compound quarterly, where n is 4, every 3 months. What's our next one? Probably monthly. We're compounding monthly. We're doing it 12 times per year. Weekly. We use 52 times per year. 52 weeks in a year. Then there is bi-weekly, which is 26 times per year, every 2 weeks. And let's see, am I forgetting any? 52, 26. I guess those should have been reversed. Oh well. And let's get to daily. We assume that there's always 365 days. We assume n equals 365 for daily. Always. Right. We don't need to worry about leap years and things like that. Let me page. Now, instead of developing the formula, because it's not quite as straightforward, I'm just going to jump in and give it to you. Okay? And so if we invest a lump sum of P dollars at an interest rate R, compounded n times per year, okay, then after T years, now notice T now has to be in years as opposed to simple interest where we just, as long as the rate and the T matched, then we were happy. Right now T has to be in years. Then the final amount, or the accumulated amount, is given by this formula. Okay? A, which is P, same old P, the principal amount that I've invested, but then it gets a little bit fancier because we're compounding. Okay? 1 plus R divided by N. What's this? I'll write this bigger here. A equals P times 1 plus R over N to the power of N times T. Oh. These guys we're familiar with. It's the accumulated amount. P is the principal investment, or the principal amount, your starting amount, right? They're not new except for N. N is new, right? It's the number of compoundings per year. And so here, N, oops, I have it here. I should just highlight it. So N is the number of compoundings per year. Number of compoundings per year. So that's why you want to have a good handle on these frequencies. Okay? In the test, I tend to use kind of common ones, right? Monthly, quarterly, daily, weekly, things that you probably remember. If on the test you're like, oh, I totally forgot what this n should be, that's not what I'm testing you on, right? And so you can just ask me, okay, I forget what compounding this frequency makes n, right? We're here to do the math. It's not really about memorizing these, but ideally you'd want to memorize them. They're not terribly hard. But in a test situation, it's stressful, right? Stressful. So if n is the number of compoundings per year and r is the interest rate, now unless it says otherwise, you can assume that the interest rate is just per year. Okay? And it'll always have to say if it's not per year. Okay? So what's this then? this R over N is, right, the rate per compounding period. The rate per compounding. R still has to be as a decimal. And then we divide it by however many times we're compounding, right? We split up that rate across the year. Okay. What about this power? So this exponent n to the t, right? And your calculator will have a power button, right? But I do encourage you to simplify n to the t first before you raise it to the power, unless you're really careful to keep n times t all in the power. Otherwise, a lot of calculators will take it to the power of n and then multiply by t, which is not what you want to do. All right, so we'll do some examples. Make sure you've got your calculator under control, tamed. N times t. N is the number of compoundings, and t has to be the years now. And so n times t is going to tell you the total number of compoundings. Right? If I'm compounding 4 times per year for 3 years, I have 12 total compoundings. And so here, n times t is the total number of compoundings. So if you have those things, then you can use the formula, right? And you can just plug things in. The hard part, remember, from last day, is figuring out what it is you're given in the question, right? That's the hard part. Figure out what you need to solve for, and then plugging it in is not too bad. Oh, that's what I had a mental note to add something here. We can solve for A. We can solve for P. We can solve for R, or we can solve for T. N is going to be given. It's really hard to solve problems where you have to solve for N. But we can solve for A, P, R, and T. Notice N will be given. So we can rework this formula. Now, A and P are relatively reasonable to solve for. Okay. R is okay, if you remember roots. Right. T is probably the hardest one, just because you need logs. And we haven't introduced logs in this course. You've probably seen logs at some point. I'm just going to give you what you need, nothing more. Logarithms. And so what I want to do is do some examples where we solve for each of these 4 things. Obviously, we can only solve for one at a time. So here we go. I'll leave a little space so that we can say, as a header, solving for, right? And it'll be an example where we solve for one of those 4 values. If $3,500 is invested at 9% compounded monthly, so that's how it'll be given to you. What will the future value be in 4 years? remembering that the future value, that's your A. So solving for A, we have this formula, and it's the only one we've introduced so far. It's going to be a major player. And so let's see here. What else have we been given? We've been given the principal amount that we've invested. And so we've been given P is 3,500. We've been given R. Notice that it doesn't specify per year, so as soon as it doesn't specify, you can assume it's per year. And so R is 0.09. It's compounded monthly. As soon as you see the compounded, that's going to be your clue that you have to use compound interest, right? So it's no longer simple interest, it'll be compound interest. Because on the test, right, you'll need to read a question and figure out, is this a simple interest problem or a compound interest problem? Because the formulas are different, right? And so as soon as you see this compounded, you say, okay, not simple interest. For simple interest, I will say 9% simple interest, right? It will say simple interest in the question. So you'll know. That sounds easy now. It's not so easy, I know that, when you're reading a question, right? To try to figure out what it is. But there are clues. So if it's compounded monthly, right, then there are 12 months in a year, so that means we're compounding n equals 12 times per year. And we want to find A, and the last piece that we have is T, which is going to be in 4 years. Remembering that T now has to be in years. Otherwise the formula won't work. You can always convert something into years, right? 4 months is 4 out of 12 of a year, right? 4/12 of a year, right? That kind of thing. Now, solving for A is P times 1 plus R over N to the N times T. And let's go to our formula sheet because, I'm going to change it because I don't like it. Do you see what they did that I don't like? It's okay. They defined I. A lowercase I is the amount of interest per compounding period. So they've just defined R over N and replaced it with a little I. I'm going to use just the formulas that we're doing in class, which means you won't need this because this will say A equals P times 1 plus R over N to the N times T. Although the lowercase I is a little bit cleaner, right? You still have to define it, and so I just don't really see the point. Push everything into the formula instead. So solving for A, we have all the pieces that we need. Can plug them in, being really careful about the order of our operations. So we get A is 3,500 times 1 plus 0.09 split across 12 months per year. And then all in the power n, which is 12, times 4 years. Right? Number of compoundings. What I'm going to do is I'm going to simplify this 12 times 4 just to be one number so my calculations don't get confused. 12 times 4 is 48. So I get A is 3,500 times 1 plus, I'm going to leave that blank just a little bit. Now this, I left it blank here, 0.09 divided by 12, because if it becomes a nice number, right, not a repeating decimal or anything like that, then I'll write it down. Okay? If it's repeating, I'm just going to keep it as a fraction and use the full number in my calculator. Okay? So let's try it. 0.09 divided by 12. Is it anything nice? Well, it's not repeating. It's just tiny. It's not nice, but scientific notation, 1, 2, 3. But it is just that. So I'm not rounding anything. People get really upset when you round with their money, right? And so you have to overpay or you don't get paid enough. Yeah. Keep all your decimal places. It's especially important for money. A lot of the time, if you keep kind of 4 or 5 decimal places, it's okay. But for money, it can make a difference. So keep all your decimal places.
Say it's mostly like if it's a repeating decimal.
Yeah. To round it. You can keep it. Yeah, do you know how to store stuff in your calculator? I can show you. I can show you after class. So what I would do, if it's annoying to write out, which I think is mostly what most people are trying to avoid, trying to not write out a huge number, right? You can just keep 0.09 divided by 12 on your page. That's fine. Because this is true. Yeah. Yeah, totally. So if you do have a big number, like if this was a bad number, you could write, I stored this in A. And then you could say, hey, instead of here, I stored this in A, right? And I'll be able to link those two. I think we'll have one where I want to keep all my decimal places later, so I'll keep it. This one's nice, but I know. So particular. So our next step, inside the brackets, right? BEDMAS, brackets, then exponents, right? And so we need to simplify inside our brackets. And so we get A is 3,500 times 1.0075 to the power of 48. So now I'm going to add 1. Then I've done my brackets. Now it's time for exponents. So now I take this 1.0075 to the power of 48. I get 3,500 times 1.4314053333. And then, of course, it keeps going. But this is a nice opportunity to show how I would use the store function, right? And just kind of indicate to me that, hey, I'm going to use all the decimal places. Don't worry. And so I'm going to store that in A, depending on your calculator, right? You might have stored in 1 or 2 or 3 or 4, right? So you want to keep all your decimal places. In this case, because we're so close to the end, you can just keep it on your screen because it'll have more decimal places behind the scenes and multiply by 3,500, and then you're done, right? And so, so you don't really need to store it, but if I was going to store it, I would indicate it like that. If I multiply by 3,500, I get 5,009.918667. I would like to see kind of all the decimal places, but then, of course, money we round to 2 decimal places. So your final answer is 5,009 and 92 pennies. Money rounds to 2 decimal places. Huh? Properly. Huh? Nice. So solving for A, right? As long as you're able to pick it out from the question, not too bad, right? And so, not too bad at all. Let's do another one. Again, I'm going to leave some space as a header. This will be an example solving for, well, let's see. I bet you can take a guess, but how much should be invested in an account paying 9% compounded daily for it to accumulate to $5,000 in 5 years? So now I have the accumulated value A, and I want to find how much should be invested, right? And so here, how much should be invested means we want to find P. Just as before, right? We're going to list all the things that we've been given just for some clarity. But we've been given the rate, 9%. R is 0.09. Compounded daily. And remember, we say daily is 365 compoundings per year. So N is 365. And it's going to accumulate to $5,000, which means A must be $5,000. And T is 5 years, right? Just checking in that T is in years, and it is, and so that's good. 5 years, right? Make sure it's in years. Check. We only have the one formula, so we can plug in the values and solve for P. A is P times 1 plus R over N to the N times T. Now I have A, I have R, I have N again, and I have T, so I can solve for P. Yeah.
On our formula sheet, there's a blank formula that has P equals. Could we use that instead?
Yes. What would it look like?
That's P equals capital A divided by 1 plus tiny I to the power of it.
Nice. So you could plug it in here and then simplify and move things over and solve for P with your numbers in there, or, right, what do you have to do to solve for P? You can use the variables, right? All you would need to do is divide A by this whole chunk, right? And so then we get A divided by 1 plus R over N to the N times T. Now on the formula sheet right now, it says a lowercase I, but earlier they defined I equals R over N. And so I'm going to change that to match what we're doing, and I'll just have R over N. But this will be on your formula sheet. That's nice. So you don't have to be comfortable moving things around. And that's why I feel okay solving for T. I'll add it to the formula sheet. I know it's not on there yet. Okay. Let's see here. Oh, I'm trying to remember. Anyways, okay, that doesn't matter. P, got ahead of myself. A is 5,000 divided by 1 plus 0.09 divided by N, which is 365 to the power of 365 for 5 years, which will be however many days it is in 5 years. Again, I would recommend that you simplify 365 times 5 just to get it to be a number, because then you can keep all your decimal places in your calculator without having to store them. And so if we start there, P is 5,000 divided by 1 plus 0.09 divided by 365. And 365 times 5 is 1,825 days. So I like to do this simplification first, because what you'll see is now I can just keep all my numbers on the screen. Because what do I need to do next? I need to do 0.09 divided by 365. 0.09 divided by 365 is very small. So I'm going to keep it as is. And then I'm going to add 1. I get P is 5,000 divided by 1.000. Let's see here, 1, 2, 3 zeros, 246575 to the power of 1,825. So I did this division and added to 1 in one move. You're allowed to do that. Otherwise, it's just a lot of writing. Then I have this number on my screen, this 1.002. I can take it to the power of 1,825, and I get 5,000 divided by 1.568225193. Now, I want to make sure that I keep all my decimal places, right? And so if I do 5,000, I have a previous answer button, right? Usually there's an ANS button, and that'll just pull up your previous answer. So if I do 5,000 divided by my previous answer, as long as you get 3,188.31761, I'm happy. As money, 3,188.32. So you need to be really comfortable working with your calculator. So make sure that you're getting those same answers, right? Because you don't want to learn bad habits. Wow. Oh. So if you're solving for P, really what you've done is just moved this lump over to the left-hand side, right? Now, let's see here. How about our next example? If $4,000 is invested at 4% compounded annually, how long, will it take to accumulate to $6,000? Huh? It does. So we want to find T. Up this guy down. Okay. Now, there wasn't a lot of moving around from the original formula to get to the formula for P. I'm going to do the moving around, but then on your formula sheet, it's not on there right now, I don't think. I think there's a formula for N, but not T. We're doing T, so I'll give it to you for T. So if it feels unfamiliar, it's okay, as long as you feel comfortable working with the formula that we arrive at, that's good. So if we have A is equal to P times 1 plus R over N to the N times T. If we want to solve for things in the power, then we need logs. The log of NT. Well, here we go. To simplify the power. I am pretty sure I also need exponent rules. Well, here we go. I need to isolate everything that's raised to a power. And so I have A over P is 1 plus R over N to the N times T. Oh, it's gonna get gross. Anyways. Now, I can take the log of both sides. Do you guys know the log? All your calculators have a log button. And so you can find it. And we'll do an example. There's different log bases. Log base E, log base 10. You can really use log base anything that you want. But most calculators have a log base 10 button. So if it just says log, it's log base 10. Or you might have seen the natural log ln button. I have a picture of my calculator from the last time that we used it. Let's see here. Where can I put this thing? It's too big. Okay. So here, the buttons that you're looking for will look something like this. You know what? Let's just use the LN button because it's a little bit cleaner. It's log base E. It's okay. Does everyone have an LN button on their calculator? Something like that? Yeah. So we'll use the LN button because all scientific calculators have one. Because most sciences work in logs. I'll delete this and I'll just move my little arrow. The natural log or log base E. Not something that I'm expecting of you, but you do need to be able to use the LN button on your calculator. Right, that's as far as we'll take it. And this was orange, but I'll change it back to blue. Taking the LN on both sides. Now, the reason we use logs, and logs are really fun, and I wish we had time to do logs properly in class, but the reason we use logs is because the natural log or any log brings this power down in front. And so that's how we bring this power downstairs. And then it multiplies the natural log of 1 plus r over n. We're trying to solve for t, and we're almost there, even though it doesn't really look like it. But t becomes the natural log of a over p divided by n times the natural log of 1 plus r over n. I should write that as a proper fraction. And I'll do this one too. Bless you. And this will be on your formula sheet. It's not right now, but it will be once I fix it. The LN button is just a button on your calculator. We have A, we have P, right? Or we have N, and we have R, and we have N again. So we have all these things. It's just going to look a little bit strange. And I'll move this down here. Okay. So in this case, we were given $4,000 is invested. Okay, so P is $4,000. At 4% compounded annually. And so R is 0.04. And compounded annually, N is just 1. Right, 1 time per year. That's nice. How long will it take? So we want to find T to accumulate to $6,000, which means A must be $6,000. Now we'll have our formula for T. And we already figured out that that's what we want to solve for. So we can write it out. The natural log or ln, some people call it ln, but I find that's confusing. The natural log or ln of a divided by p divided by n times the ln of 1 plus r over n. We can plug in these numbers. The ln of 6,000 divided by 4,000 divided by n is 1, which you don't have to write if you don't want to. It's just gonna go away anyways, but I'll write it there for completeness. 1 times the ln of 1 plus 0.04 divided by n, which is 1. Okay. What you want to do when working with these ln's, you want to simplify completely before taking the ln. Simplify inside completely before taking the ln. Now, depending on your calculator, sometimes it'll want the number inside the ln on the screen and then you hit ln. Mine, I hit the ln and then I can put in 5 and I get 1.609437912. For example. I'm going to simplify 6,000 divided by 4,000 is 1.5. So I get t is the ln of 1.5. I can drop the 1 now because nothing's really happened. Simplifying inside this ln, I have 0.04 divided by 1, that's just 0.04, and then plus 1. So now I have the ln of 1.5 divided by the ln of 1.04. Now, just so you can make sure that you have tamed your calculator, I'll write out what each of the ln's should be, but you're allowed to just skip to the end if you want to. Right? Just because I find it's easier to work with a lot of calculators by just forcing it in. Right? But the ln of 1.5, I get 0.4054651081. And then the ln of 1.04, I get 0.039220711315. Yeah.
Very awesome. Calculator, what is the ln? Like, does it multiply by probably by pi or something?
It takes the logarithm base e, which it just takes the logarithm base e. A funny story about logs, though, is so when I told my grandpa that I was doing my undergrad in math, I was like, yeah, I've decided I'm going to do math. And he was like, like logarithms and stuff. Because logarithms used to be really, really difficult to do by hand. Right now, our calculator just does it, and it just does magic in the background. Okay? But it used to be really complicated. So he was like, ah, yes, logarithms. Let's probably what you're doing. But we're so used to it just being a button and it just does secret stuff. And it just does it. So, here we go. I'm gonna do it start to finish in here. The ln of 1.5 divided by the ln of 1.04. And I get a t of 10.33803,507 years. And let's not bother converting the 0.338 into months or anything crazy like that. Just keep it as a decimal. Nice.
Do
Yeah.
you want us to go over the decimal? Like maybe-
For the years, let loose. Show me all of them. But you don't have to do any rounding after. Yeah. Nice. Okay. I'll add a page here. I think it needs its own page. I think the last one's going to be, we've solved for A, we've solved for P, we've solved for T. Of course. But let's confirm. If $5,000 is invested now for 6 years, what interest rate, find R, compounded quarterly is needed to obtain an accumulated value of $8,000. Just like we did with T, I'm gonna show you how you massage the formula, but as long as you're okay jumping in saying, hey, I need to find R, where's that formula for R, and using it, that's great. Okay. So A is P times 1 plus R over N to the N times T. I want to isolate R. What I first need to do is I need to get these brackets and the N to the T on its own by dividing both sides by P. Now, to get inside the brackets, I have to remove the power, right? And to remove the power, I need to take the root. So here, to remove the power, we need to take the root. In fact, we need to take the n times tth root. The n-th root. That sounds gross, but it's actually just going to look like this. You've probably seen the square root, right? What you can have is this little, in this crook, you can put any root that you want. And so here, oops, I need room. Come on. If I take the n times tth root of both sides, that's how I cancel this n to the power of n times t. Okay. And so really what I need to be able to do here is figure out how to solve for this. And because not all calculators, some calculators have, you can just tell it what root you want, right? It'll just have a blank space for the root. But most calculators don't. I think, not to brag or anything, but mine does have the, no, it doesn't. Well, so much for bragging. Well, I need to work this as well. So we calculate a to the power, or a divided by p to the power of 1 over n times t. So as an example, if you want the fifth root of 3, that's going to be the same thing as 3 to the power of 1 over 5. So as long as you're okay putting things to the power, which we've already been doing, then you can put in a power as a fraction, right? And that'll be the root. You can also kind of talk your way into how that would cancel the n to the, or n times t in the power over here, right? And so, but we don't need to worry about that. But what we're left with here is just the basic 1 plus r over n. We're getting close to that r that we wanted. Now here's where we need to rearrange a little bit, or I guess a lot. First, I'm going to subtract 1 from both sides. Okay. I am also going to do my classic switcheroo, where I have the, oh, I'll move this here. A divided by p and the nth root. Oh, bless you. Minus 1. Notice that I put this little crook here. Sorry. Little crook here to indicate that that's the end of the square, or end of the root, and then minus 1. So now I've moved this 1 over here, and now the last thing I need to do is multiply both sides by n. And so I get r must be n times the n times tth root of a over p, then minus 1. No, I'll highlight it. It's on your form. It will be on your formula sheet. I think they're not on there right now, because I didn't catch it, because I thought, oh, all the formulas, they're all the same. We all use the same thing. No, we don't. So I'll put these on here. And we are not going to solve for n. You can if you want to, but we're not going to. Okay? And then, yeah, the rest are. So this will all, I'll update this with the highlighted ones, just like we've seen. So you don't need to remember how to do it. You do need to remember how to plug things in, right? And how to use your calculator. So in our example, what were we given? We're given P is 5,000. T is 6 years, making sure that T is still in years, right? Don't fall for that curveball. 6 years. Right, make sure, okay, it's in years, that's good. We want to find what interest rate, so find our compounded quarterly. Now quarterly means n is 4 times per year. And we want to obtain an accumulated value of $8,000. So we want A to be $8,000. So we've set a time frame. We have our initial $5,000 and I know I want $8,000. The bank says, well, we compound quarterly. And then you'll be able to say, well, then I want this rate. All right? So what is the rate? Let's see here. R is n times the root of a over p, the n times tth root, then minus 1. Oops. I'm used to doing square brackets there. I don't know why I went for round brackets. Oh well. Committed. Plugging in our values, n is 4 times, and you'll want to give yourself, I didn't give myself enough space here for the n times t, so 4 times 6. Oops. What a gross root. There. 4 times 6th root of 8,000 divided by 5,000, then minus 1. Same as before. You know what I just realized? Should I be nice on the formula sheet maybe? Or n times a over p to the 1 over n times t, then minus 1. That might be nicer, since I'm changing it anyways. No? You like seeing the root? Here, I've done it for you. How about I give you both? Or r is equal to, I just have to remember to add those. Then you really don't have to remember the root stuff. But you do need to simplify 4 times 6, n times t, right? N times t, 4 times 6, it's 24. So I have r is 4 times the 24th root. And how about 8,000 divided by 5,000? Is it anything nice? Of 1.6, that's nice. And then minus 1. This is 4 times 1.6 to the power of 1 over 24, then minus 1. I wrote 25. Gave myself just one extra compounding. Bad, Emily. Okay. Where are you going to start? You're going to start here, right? 1.6 to the power of 1 over 24, then minus 1, then all that times 4. Right? I'll show my work in the order that you need to do it. So 1.6 to the power of, and then I like to put brackets when I'm working with fractions up here in the power, put brackets around it just to make sure it holds it as one number. 1 divided by 24. This becomes 1.019776499 minus 1, which I would store, but I also see the end of the tunnel here because I'm just going to subtract 1 from this so I can keep it on the screen, and then that I'm going to multiply by 4. So I can actually just work with the numbers on the screen. So r is 4 times 0.019776499, and then I get a couple more decimal places, I guess, 899. And then finally times 4, I would need an R of 0.079105995556. Need a rate of approximately 7.91%. Let's do 1. Yeah. Question. Uh-oh. Let me just quickly rework it in case I did something weird. I'm starting here, 8,000 divided by 5,000 to the power of 1/24. Good. Minus 1 times 4. I get the same thing.
Yeah.
Does it look like that? Yeah, so you want to make sure that the budgeting part is. Otherwise, it'll just do 1.6 to the power of 1 and then divide by 24. Yeah, so that put you here. Nice. Yeah, make sure you get your calculator under control. All right. I haven't been writing little summary answers at the bottom of them all. The only reason I did it for the rate is because usually we report rates as percentages. But of course, if you just end it here, I'm happy, you're done, right? This is correct. This is your R, right? But if you want to think of it as percentage, 7.911%. Nice. So those are the 4 different scenarios using the same formula, right? I'll rework it for you, right? But those are the 4 things that I expect you to be able to solve for, right? Given all the other things. Now I need to check, okay, good. Okay. Let me add a page here. The effective interest rate is kind of a special interest rate that allows us to compare interest rates, right? Because 4% compounded annually is going to be different from 4% compounded daily, for example, right? And so it'll behave slightly differently. And so the effective interest rate is, I actually don't know if this is true in Canada. I'm pretty sure it is. But in the States, banks are required to state their interest rate in terms of effective yields, or the effective interest rate, or for us, we use the term APR, which is why I think banks have to publish the effective interest rate, APR. Okay. And so the effective rate is also called the annual percentage rate, APR. So the effective rate is the interest rate compounded this is missing a what is what. Let's see if that makes sense. The effective rate is what the interest rate compounded annually would be equivalent to, is the interest rate. How do you make this make sense? I know what they're trying to say, but I don't know how to clarify it. Let's see, let's try. So the effective rate is going to be the annually compounded rate that's equivalent to the stated rate with the compounding periods. Right. I'll erase this because I feel like it didn't really clarify it. And so here, the effective rate, I'll just write my own interpretation here, or my own definition, I should say. The effective rate is the annually compounded rate equivalent to the given rate and n. The reason we want it is so that we can compare annually compounded rates. Effective rates allow us to compare rates because they are all compounded annually. So to examine several investments to see which has the best rate, we find and compare the effective rate for each investment. And then if we're investing money, then you want the highest rate, right? Where's the first part of this? Weird. Did it go somewhere else? No. The reason I am hesitating is because it starts at 2 here, but I don't remember seeing a 1. Weird. They must have compiled. I don't know. I'll have to go back and find it. Clearly, I cut it out for a reason. If a bank pays an interest rate R per year, compounded n times per year, then the effective interest rate is given by this formula here. So usually we denote it with an R subscript EFF for effective rate. And the effective rate, you know, is compounding annually. And so it's going to be 1 plus R over n, that looks familiar, right? To the power of n, and then minus 1. So, knowing that, let's do an example. If Bank A pays 7.2% interest compounded monthly, what's the effective interest rate? Let's start with that. So Bank A, we want to find R and then a little EFF at the bottom there for the effective interest rate is 1 plus r over n to the n minus 1. There's not a lot of information that we need, right? We were given that r is 0.072 and compounded monthly means n is 12. That's all we need though, to find the effective interest rate, which is 1 plus 0.072 divided by 12 to the power of 12, then minus 1. A really common mistake is that you forget to minus the 1 because there's a lot of work that goes into the first part, and then you forget the minus 1. But just as before, we're going to simplify the 0.072 divided by 12, then add it to 1, and then to the power of 12, and then subtract 1. So here we go. 0.072 divided by 12 is small but nice. Is 1 plus 0.006. 1, 2, 3, yeah. To the power of 12, then minus 1. 1.006 to the power of 12, then minus 1. Now I can do that part. Yep, sorry.
Should this be on the,
Yeah. It'll be on the formula sheet. Don't worry. I'll highlight it. There. Okay. 1.006 to the power of 12. I get an effective rate of 1.0744244168 minus 1. Right? A rate of 1.07 is 107%. You could try telling a bank that that's what you want, but they're probably not going to do it. Right? 100% of your money and 7%. No. But take away 1 and all of a sudden they're very similar. 0.07442416772. What you'll want to make sure when you find the effective rate, it should be kind of similar to the rate that you have here initially, right? 7.2 should be around 7, and we find that it's 7.44. So 7.2% when it's broken up and compounded monthly is going to behave the same as 7.44% compounded annually. That's what the effective rate says. So here, therefore, 7.2% compounded monthly is equivalent to approximately 7.44% compounded annually. If Bank B pays 7.25% interest compounded semi-annually, what is the effective interest rate? And then which bank pays more interest? Right, and so with the effective interest rates, we're able to compare them, right? Apples to apples, annually compounded to annually compounded. And so for Bank B, we want to have, let me just grab the information so I don't have to do it again. Wait, so small. There. R is 0.0725. Compounded semi-annually, that's kind of a tricky one to begin with. That's n equals 2. Right? And we want to find the effective interest rate. 1 plus the R over n to the n, then minus 1. One plus 0.0725 divided by 2 to the power of 2, then minus 1. 0.0725 divided by 2 is, let's see here, 1 plus 0.03625, then to the power of 2, and then minus 1. Plus 1. 1.03625 to the power of 2, then to the power of 2, 1.0738140063 minus 1. As soon as I see this kind of, sorry, yeah. As soon as I see this kind of 7-ish%, I feel good about my answer, right? I'm gonna subtract 1, but I feel good that they're very similar, right? So I'm expecting them to be similar, and they are. Now question, yeah.
Do we have to do the 1 plus like the R over n if we are minusing, so taking the 1 away at the end? Could they not technically cancel out? Or would it be different because
Because it's to the power of 2, we can't take minus 1 inside the brackets.
So what could you cancel out the 1 still? Like the 1 plus
Like this one?
numbers, yeah.
And this one? No, because we've got this power of 2 that's locking in the 1 plus. So we can't do that. Yeah. You can try it. You'll find that you get weird answers. Yeah, just make yeah, because it's inside the brackets. Cannot with the power. But good, because I can see how that would be very tempting. What does this mean? That means that 7.25% compounded semi-annually is equivalent to 7.38% compounded annually. And so therefore, 7.25% compounded semi-annually is equivalent to approximately 7.38% compounded annually. Now, because these effective rates are both compounding annually, we can choose one, and we would want to choose, well, in this case, if we're investing money, right, then we want a higher rate. If you're borrowing money, you want a lower rate, right? So it depends on what you're doing. But in this case, for investing money, I would prefer 7.44% instead of 7.38%. Whereas if I'm borrowing money, of course, I want the 7.38 instead of the 7.44. Therefore, for investing money, I would pick bank A. Nice. Okay, I have a feeling this will not be tested. So don't worry. Because I'm out of time. So I won't test you on it. There are some questions on it, so I will talk about it just briefly because it's kind of a cool concept. Mind-boggling. But interest can be compounded yearly, semi-annually, quarterly, monthly, daily, right? We've seen all those. But a cool thing is that we can have continuous compounding, right? Continuous compounding is just every moment it's being compounded, right? You got a little bit of interest, a little bit of interest, a little bit of interest, right? And so it gets a special formula, okay? Where A is P times E. E is 2.718 something. There's an E button on your calculator. To the power of R times T. Now what I'll do is I'll fill in the solutions to these. We can find the effective interest rate. It uses E, the E button. It's a constant, kind of like pi. But so you'll have some practice problems, but for continuous compounding, I won't test you on it. With that, I release you. Been a long night. Yeah. Yeah, you bet. If you have any questions, let me know. I will stop the recording though. Let me just, I'll get you back there.